but I'll try and I'll try and stay still. I won't succeed, but I'll try.
So, welcome everyone, and thank you for coming to the fourth PLanQC workshop. So, there's been some recent development in quantum computing when we have more powerful quantum computers with better qubits. And the question of today is how to best program them, how to best optimize them, and how to best verify quantum programs. So we'll have Conor McBride today talking to us about some of the monoidal adventures. I don't know what it entails yet. And I will give the floor to the speaker.
Right. Okay, well, thank you very much for inviting me. This is another fabulous instance of Ross Duncan getting me into trouble, for which I'm always glad. The last time I spoke at an ACM thing, it was on Sunday, the 18th of August, 2019, in Berlin. I was keynoting type-driven development first thing in the afternoon, and I recall making some morbid jokes about which of my organs was going to stop working first. But I also remember having an excitable dinner chatting with Jennifer Pakin about a project with Ross that was about to kick off as a knowledge transfer partnership with the University of Strathclyde and the company that is now Quantinuum. And yeah, nearly 3 weeks later, on my way to the kickoff meeting for that project, I had a heart attack. And I was outside their offices, which were in Cambridge Union Society, and I was thinking, is this where I'm going to peg out? Outside this Tory factory debating club? You know, how embarrassing. And just the thought of dying on that particular spot gave me the will to survive. And, but yes, that knowledge transfer partnership kicked off 4 years ago. We hired Craig Roy, who's up next, and we started working on a programming language for organizing quantum experiments, which was an interesting foray for me as a type theorist into designing programming languages to prioritize the monoidal structure that we need for circuit construction over the usual kind of Cartesian closed structure, you know, one input, one output, higher order programming that people are used to working with in functional programming languages. It's not that the higher order Cartesian closed structure isn't there, it's just that when you want easier access to the monoidal structure, you make perhaps different choices about where to spend what sorts of syntax. So, okay. It's also, you might find yourself being slightly more careful about how to organize the information flow. So I'm going to talk about the ins and outs of making things fit. Because if you've got more qubits, you've got better qubits, you can build bigger things. And how do you build bigger things? Well, out of smaller things. Once things get big enough not to be monolithic, then you need to organize stuff. You need pieces to fit together properly. So we need to start thinking about kind of type disciplines for fitting circuits together properly. And that means thinking a little bit carefully about the way information flows through a type system. So this is a little joke about category theory, that, you know, here's the sort of situation where if you think categorical morphisms know their domain and codomain, then they are kind of jigsaw pieces with two outies. and they don't really fit together properly. You have to figure out, you have to have some extra adapter thing in the middle. So this is how set theorists think categorical morphisms work. Meanwhile, type theorists think categorical morphisms work this way, where the source and target of the morphism are dictated in advance, and you say which things connect them. But these pieces don't fit together either. The fun things that do fit together, as you can see, are the things where you get told, the source comes from outside the piece, but then the piece tells you its target, ready to compose on the next piece. So this is the kind of Estonian way of talking about categorical morphisms, and it's the one that's actually compositional. So these are the kinds of considerations that I'll be getting into, and I should be very careful, and the number of waste pages I've already thrown away because I drew the types in the wrong place. I'll be very careful to make sure that types that are intrinsic to things are inside the boundary of the diagram that represents the thing, and that types come from outside are outside the boundary. So I'm being extra careful to keep tight grip on the information flow in the type system. And it's an interesting exercise. I mean, lots of functional programmers from the 1980s onwards are used to saying, let's just generate a lot of constraints and solve them. The sort of global constraint solving with unification variables has been kind of how it's done. And I'm trying to figure out, I'm not promising not to do that ever, but I'm interested to see just how neat we can make type systems just by managing local checking only, just by managing more carefully the propagation of information from one place to another, rather than by inferring it from nothing. So I'm hoping to tell you stories about 3 of my monoidal adventures, which might hopefully set Craig up. He's going to show you some actual quantum programming with Brat. I'm going to talk about the ideas behind how its type system works. The Brat is the language that we've built. So first of all, I'm going to just talk about monoidal stuff. Here's my favorite monoidal category. I'm going to try not to be too heavy on the terminology. It's seen from bottom to top. It's the thinnings. It's about how to insert things between other things. Seen from top to bottom, it's about how to select some things from other things. So this whole picture, you can see I've selected 4 of these wires from these 7. So these things, these sort of notions of selection, you can plug them together from side to side. So for example, if I select 2 from 3, and if I select 4 from 4, together that's selecting 6 from 7. But I can also compose them end to end. So here I select in the top half, I select 6 from 7, and then I select 4 from 6. So that's selecting 7 from 4. If you think the notation looks like binomial coefficients, that's not an accident. And we note that, in fact, these things are representable by bit vectors, where the top number is the number of bits, and the bottom number is the number of ones. So length and population count. And these things indeed have monoidal structure, that's the side-by-side structure, as well as compositional structure, that's the top to bottom. And used upwards, these are really great for doing Kripke semantics of lambda calculi, but that's a whole other story. Used from top to bottom, they're a good way of selecting some of the things you're interested in. So for example, if you've got a whole load of bits, and you want to say, oh, I want to feed this selection of the bits into this component, and frame out the rest of the bits and get them back later, then this is a good way. These things are a good way to say, These are the ones that I'm interested in, and then where the zeros are tells you where the things you're framing out. Every thinning gives rise to a partition of all of the inputs into the selected ones and the unselected ones. Okay, so that's why there is some reason for us to pay attention to these structures. Anyway, so it's really straightforward, right? You can clearly count all the bits, and you can clearly count all the ones. So if I give you a concrete actual thinning, you can figure out what its type is. On the other hand, if I want to add the categorical operations, the identity and the composition, then I have a slightly harder time. If I want to say there's always an identity thinning, and I want to figure out what the numbers are, then I need to know, I need to label it, I need an annotation to tell me how many inputs I'm keeping all of. Right? There's no way I can figure out, there's no way I can deliver these n's intrinsically unless this n comes from somewhere. So the identity needs an annotation. Meanwhile, if I'm composing two things, there's no reason a priori why they should meet in the middle. I have to check a constraint that the number coming out of the top is the number going into the bottom. So annotations on identity, constraints on composition. If I do it the type theorist way, and I say, no, we're going to specify the numbers in advance and just check that the constructions are okay, then if I say, I want the identity, there's no need for an annotation. The trouble is that we need to check that the number of inputs and the number of outputs are the same. Meanwhile, if I'm trying to check a composition, there's nothing that's telling me the number in the middle. I know the number at the start and the number at the end, but I don't know how to check the components unless the semicolon is labeled with a number to put in the middle. So again, bad news. The type theory way of checking the categorical structure doesn't work either. So what do? Well, one thing we can do is the kind of 1970s text adventure story. It's like, you are at N, what would you like to do? Stay still. Well, in that case, you're still at N. You know, you are at M, where will you go? Oh, I will choose theta. You are now at N. Where will you go? I will choose phi. You are now at L. So you get told where you are and which ways you can go from there, but you don't find out where you're going until you choose one. So this way you can do identity and composition without any constraints or annotations, which is fabulous if all you want is the categorical structure. But we want the tensor structure. What about the comma? All right. So some compromise will be necessary, but the basic picture is this one, is that we start to see whether we can hang a component off our prefix of the inputs we know about. And if we are successful, if this component fits as a prefix of the available inputs, we get told both what comes out of that component and which inputs are left over, or rather right over, as I'm fitting on the left. So in come the inputs, and then as outputs to our compositional type checking process, we find which are the things below us to connect onto, and which are the things still to the right of us that we haven't used yet. Okay, so let's see what happens. For a single 0 component, we use up one input. 0 doesn't deliver any outputs, and we've got one fewer input left over. So yeah. So 0 deletes one input. 1 preserves one input and leaves the rest. The monoidal unit consumes no inputs, delivers no outputs. Then to check a tensor, f comma g, we first of all check what F consumes, see what's left over, and then feed that to G. And whatever's left over from G is what's left over from the whole thing, and then we can add up the number of outputs that come out. Meanwhile, we've got a little bit of a compromise here. We've got, there's no way, if we're allowed to not consume all the inputs, that the identity is good without an annotation. We can't just have a kind of randomly stretchy identity. We do need to know how many inputs we're consuming so that we can figure out how many inputs are left over. And then for the composition, we check that the first component, that our F, fits under our inputs M, leaving M prime over, and then we better check that our second component, G, uses all of the outputs that come out of the F. So we insist that the right-overs in the lower component are 0. So again, we've got another constraint, but it's a straightforward constraint. So this is a reasonable compromise. And you can imagine trying to infer the annotations on the stretchy identities just by constructing a system of linear equations and checking whether Gaussian elimination gives you a unique solution. So there is a sort of sensible global constraint solving approach that might simplify this in many circumstances if you're willing to switch it on. But even if you're not willing to do that, this is still pretty good. Okay, so that's the thinning story. I would point out, I should check the time. What time is it? It's about the time I hoped it would be. So you can play this game in multiple dimensions if you're interested in checking kind of matrix-like things, and you've got some column headers and some row headers. Then you can ask, does this rectangular thing fit in the top left corner? And if so, which right corner comes out and which lower corner comes out? And then if you want to do horizontal juxtaposition, you try and fit things into the right corner. If you want to do vertical juxtaposition, you fit things into the lower corner. So there's a perfectly sensible approach to just tiling spatially, just playing the same, what comes out, what are the right-overs, in however many dimensions you need. So that's the basic trick, which I will be doing ad nauseam. Okay, so that's the end of adventure 1. Let's do adventure 2, where we're in the business of monoidal functional programming. And the basic units we'll be working with are things which do something to some inputs to get some outputs. And I'll be calling those things verbs and drawing them as rectangles with input wires and output wires. And in BRAT, we're in the business of managing these things with inputs need not just single types, but a type that represents a row of input values, and likewise a row of output values. And there will be some dependent types showing up in due course. So some of the types further along in the row will depend on values earlier in the row. So we need to make sure guessing dependent types is tricky stuff. So we're not even going to try at the moment. So what's crucial, I'm not going to insist on exactly a fixed discipline of, we need to know the inputs, we're going to tell you the outputs, or whatever that happens to be. We can be a bit more relaxed about the way the information flows, as long as the information is somehow there. So crucially, every vertical interface, that's to say everywhere we're doing a composition, we need to make sure that the information is either coming from above or from below. We don't mind, we can propagate the type information in either direction and play the same right-overs trick to manage the tensor structure, the commas. We don't really mind if the information comes from above and below. We can check that things are consistent with each other. The situation we're desperate to avoid is where we've got no information at all. But we can still manage quite a lot. Okay, so this is the usual business. This is basically, this technology allows us to plug together things that look like circuit diagrams, connecting inputs to outputs. But it's also the case, I mean, especially if the wiring is fiddly, that, you know, sometimes we want to do ordinary functional programming that, you know, gives names to things. So verbs are about doing to inputs to get outputs. We also have nouns. Nouns are about being. I always write them with a curved top because they have no upward connectivity, but they have downward connectivity. They tell you what a bunch of stuff is. And then we will also have patterns, which analyze inputs and give names to components of it. So patterns are about seeing. So we've got verbs for doing, nouns for being, patterns for seeing. And we always ensure that when we're analyzing patterns, that there are types specified from the outside. And in particular, that ensures that whenever we are using a pattern variable to give a name to a thing, the type of that thing is known. So that when we turn it upside down as part of an expression, anything with a name is a noun which knows what it is, knows its type. So the type flows into the pattern variable upside down. It's now intrinsic to the uses of that variable as an expression. And we will have nouns that we check and nouns for which we synthesize types, but it's an excellent start that all the things with names know their types. Okay, so that's the discipline. Right, and now I'm going to spend a little bit of the profit from that discipline on managing the application notation. So an application is a noun which feeds a noun argument into a verb function. So it checks like this. I can type check an application of F to A if F is a verb which knows its inputs and its outputs, and then I can use those known inputs to check the argument, and I can also deliver the known outputs. But where do I get my function from? Well, it might, for example, be a function with a name, in which case it will actually be a noun whose type is this. So this is, when you see the braces, that's a higher order value. This is a value, a noun, of function type. It's a knowing how to do the verb rather than actually doing the verb. But because it's a noun used in a verb position, and because we know its type, we know without any extra syntax how to use F. So the forcing of this, we call these things thunks, right? The knowing how to do it but not actually doing yet is called thunking. So forcing a thunk of known type is reassuringly silent. So that's an example of how we carefully make sure type information turns up where we need it in order to spend no extra syntax. There's extra syntax here indicating application, but no syntax for forcing. Meanwhile, if we want to construct functions, we expect types to be specified from the outside, and we have explicit thunking. So curly braces, the joke about braces being suspenders is appropriate here. So we can make a noun by suspending a verb. We better know the type, and then we're going to type check the verb against known inputs and known outputs. And indeed, this verb might be, but doesn't have to be, a pattern inspecting the inputs, binding a bunch of variables, which might show up in a noun delivering the outputs. So yeah, your traditional lambda abstraction is one way of making a verb by naming bits and pieces of the inputs and then saying what the outputs are. So seeing the inputs, being the outputs. Okay? Right. And then the fun thing is that we play the same game for quantum kernels. So also a value type in the Brat world are types of circuit designs which are resource neutral. So, the idea for a circuit design is a perfectly replicable thing. There's no problem about copying the idea, right? As long as we're not copying things which are resource bounded like qubits. Although these days we can also have some classical bits inside the machine, and those things are copyable. So so the resource discipline associated with this lollipop basically secretly bangs any classical data that are inside the machine. And we use exactly the same syntactic and type checking technology for managing the monoidal structure, the tensor and the composition, and the same sorts of typing discipline. And then once again, when we're building a kernel, you've noticed I'm using Roman letters for types of things in kernels, and it's a completely separate world of types for signals that live in quantum computers from higher order values that live in functional programs. So that's a very careful separation. So when we're building kernel verbs and Brat nouns show up, again, with known type saying, oh, I'm a kernel design, then once again, you get silent forcing, slotting the circuit design that has been classically computed into the place where it goes in a kernel. So again, careful management of which type information we're sure to know gives us silent splicing of computed kernel designs into position. Okay, so that's my second adventure, and I'm still remarkably on time. So I want to talk a bit about what's going on in these Brat function types. I promised you a bit of dependency, and now it's going to show up. We certainly want to be able to write polymorphic functions, but we're also interested in being reasonably tight about the sizes of things. So at the moment, we are allowing a limited form of dependency on values that live in kinds rather than types. So there's a type-kind separation. Kinds are types of types. Sooner or later, everything will be a kind, and then we can just throw the types away. But for the time being, we have kinds, and we are careful to distinguish parameterized Brat types. So star is the kind of Brat types from dollar, which is the kind of kernel types. The dollar is to indicate that there might be some sort of resource involved. And then we've got hash, which is the kind of numbers. And because we're very careful to do kind checking rather than kind synthesis, we can overload type constructors that might make sense in different ways depending on whether they're supposed to be constructing a Brat type or a kernel type. And in particular, vectors preserve the world they live in. Brat vectors have Brat elements, kernel vectors have kernel elements, but they also have a length. So that means we've got a type-level notion of length, which also, so type-level lengths also have to exist at runtime. They have to be runtime values, but we need to figure out how the type system copes with them. So here's a fun puzzle. What's just happened?
Nothing.
Oh, we're stuck. I turn the page. And it's only happened once. Have I done something? It's them. Okay. I don't think it's... Okay, but we're upside down. We'll be back in a minute. Anyway, so the puzzle, I can do this is a wordy slide, right. is how to design the language of lengths, of numbers that show up in types in order not to have a miserable time. I mean, of course, there are all sorts of fantastic things you can do with numbers. And if you want to manage a type system with kind of arbitrary numerical expressions in them, well, good luck to you. You might, send all the constraints to a SAT solver and hope. Or you might kind of do arbitrarily large amounts of theorem proving. As ever, my inclination is to say, well, what can we manage without switching on any of that heavy machinery just by being neat? So, clue number one, these numbers aren't general purpose numbers. They're intended to explain how things scale up. So, we would quite like our functions to be monotone and boring. Right, another perhaps controversial suggestion is that the great simplification can be achieved if you have the good fortune to be able to use structure instead of arithmetic. Now, we don't know if we'll get away with this forever, but we're certainly going to try. So if, instead of having a vector of two lengths added together, you can keep that as a pair of vectors, or instead of doing multiplication of lengths of vectors, you just have a matrix, then you are down to functions in one variable. So that's a significant simplification. And then finally, the real clue is to think, well, we're going to use these numbers for lengths of vectors primarily. So the way we want to take the vectors apart tells us, repeatedly, tells us the ways we want to put the numbers together. So how do we want to take the vectors apart? So I kind of cooked up some hand-waving notational possibilities for how to take vectors apart. We might want to check whether a vector is empty. That means we need to represent length of 0. We might want to take a single element off the start or off the end. So we need successor. And by the way, as anyone who has ever taught functional programming to undergraduates knows from the amount of confusion they found in the room, the decision to use a symmetrical symbol for the non-symmetric cons operation has questionable virtue. So I like to put the commas at the ends where the single elements are, and sort of something horizontal where we're expecting 0 or more things. Right, so then this thing is for splitting an even length vector in half. So the equal signs are meant to suggest that what's on either side have the same length. So that means we need doubling. And then, so if you've got an odd length, it's very easy to take one off the start and chop the rest in half, or off the end and chop the rest in half, but it's perfectly sensible to want to fish the thing out of the middle of a vector of odd length, so we'll need a thing for that. And that means we need 1 plus double. And then this other gadget, of course, you might want to, instead of halving and chopping, having a beginning and an end, you might want to deal out the things in even and odd positions. So that's to say, paying attention to the least significant bit rather than the most significant bit. So again, that needs doubling. And of course, if we're going to double repeatedly, if we're doing a kind of divide and conquer, split the problem in half scheme, then we're going to need exponentiation. So my first attempt at a language of type level numbers is this one, numerical expressions. I've got a single variable, I've got 0, and I've got a bunch of ways to make bigger, which is 1 plus 2 times and 2 to the power. and I got some equations that explain how doubling and exponentiation compute. But then the point is, I need to be able to work backwards. To do my pattern matching, I need to ask, are you zero or successor of something? I need to ask, are you even or odd, and what's your rounded down half? Okay, so the good news is that 2 to the power is really easy to tell even from odd. Because we can tell, 2 to the power of something is odd or even accordingly as the something is zero or successor. And if we've made sure we can always tell zero apart from successor, then job done. But the nuisance is answering zero or successor for 2 to the power. Right, well, the easy bit is that it's always a successor. The hard bit is what it's the successor of. Can we explain how to deliver the predecessor in this language? Well, it's pretty tricky because it's 1 plus 2 times the predecessor of the previous power, which means the numbers have got smaller, but the problem hasn't. We still need 2 to the something minus 1, and we haven't got it. So, brainwave, if you can't fix it, feature it. Instead of adding 2 to the power, add 1 less than 2 to the power. Add the full size thing on n bits. So full of 0 is 0, full of 1 is 1, full of 2 is 3, full of 3 is 7. So in particular, full of 0 is 0, and full of 1 plus n is 1 plus 2 times full of n. And now it's really easy to tell 0 from successor, and it's really easy to tell even from odd. So this is a language which admits constraint solving at the moment directed. Well, what if you use a vector of functions in a verb position? Well, what you do is you push the vector constructor into all the types in the input and the output rows. So our silent forcing becomes silent vectorization. So that's to say, vectorized application is silent, but replication of individual things is explicit. We say how many you want. And that will give us not only map for 1 input, 1 output functions, but map for row of inputs, row of outputs. And at the moment, you'll see Craig has to implement map the usual way, because we haven't done this yet. But it seems like another way to get paid for bothering to make sure types turn up when we need them. Okay, goodness me, it's the first time in my life I've ever been almost on time. So yeah, I've got plenty of other stuff, but okay, my key messages are that it does make sense to rethink functional programming, to prioritize working with monoidal structure, and maybe spend slightly more syntax on supporting the kind of higher order Cartesian closed structure. And even before you switch on kind of clever global constraint solving machinery like kind of unification and SAT solving and Gaussian elimination and whatever you feel like doing, just being a little bit more careful to manage the flow of type information locally gives you a hell of a lot that's just checkably local. And if you're a bit neat, you can make the stuff that you want to be cheap silent just by figuring out where else you need to be explicit to pay for it. So yeah, global constraint solving. I'm not saying we'll never do it. Sooner or later, we'll just get fed up writing those extra lengths and those extra types, and we'll, bolt on some kinds of solvers. But it's really interesting to see how far we can get without flipping the big switch on the wall. Meanwhile, I've been having several other monoidal adventures recently. I'm very interested in types of tensor structures, particularly if they're indexed over other sorts of tensor structures. I remember years ago, somebody asked me, there must be loads of dependent types in spreadsheets. And so you can imagine that, yes, a spreadsheet is made sense of in terms of the data in its row headers and its column headers. The things in the cells tell you something pertinent to about an individual in one row and an individual in one column. So we're interested in kind of higher dimensional rectangular structures indexed over elements of lower dimensional rectangular structures. Now, you can imagine a three-dimensional array being pointed into by kind of spreadsheets on all of its faces. So this is the thing that jacks up through the dimensions. How on earth do you do it? I've been thinking quite hard about that, about kind of brick-shaped data structures indexed over other brick-shaped data structures. And the other thing I've been thinking about is if I ever want to prove anything about these programs that live in the monoidal world, I'm going to want, at the minimum, not to have to pay for the kind of intuitive string diagram deformation intuitions that we have about when two string diagrams are really telling us the same stuff. So if we're actually building that stuff out of commas and semicolons, then we really don't want to have to be shoving those things around to see if they're the same diagram manually. Correspondingly, I'm really interested in building, in finding good normal forms for these things. And it seems like you've got to do some symmetry breaking. So basically it goes, yank a wire and see what you find, right? If you find you've yanked a wire that goes all the way to the output, then great, but you've also split space in two and trapped a bag of scalars. Meanwhile, sometimes when you yank a wire, you find you've actually got a component, and then you need to think, well, okay, who's consuming the outputs of that component, and what other inputs do those things demand? So you end up building things which talk about how you use the inputs you've got, and which other inputs you needed to finish that job. So you end up building shapes that look a bit like staircases. So there's definitely some progress happening there. I don't know, I'll finish with an anecdote. I used to sort of teach all day on Friday mornings and then walk into our research lab, Livy Tower 1310, some of you will know it, and I would occasionally walk in and bellow, "Is anyone in this room not working with monoidal categories?" And then I looked around and they just, no is basically the answer. So yes, the monoidal adventures continue thick and fast. And I hope you have fun when you actually see some real brat programs coming up in a moment. I'll stop there.